Okay, in this video lecture, I'm going to start chapter 4, arrangement of electrons in atoms. And so in chapter 3, we kind of got through like what is an atom, what is an atom made up of, and talked about the atomic theory and which statements don't really hold true anymore. Well, this chapter is all about the electrons. And remember, electrons are going to tell you like how reactive an element is. And so we're going to look at the arrangement of electrons in this chapter. We're going to talk about the development of a new atomic model, just because of how electrons, aka light, can behave, and then kind of go into like the quantum theory of the quantum model of the atom, I should say. And so like chapter 4 can be kind of trippy just because it's just hard to conceptualize sometimes. So let's just get started. So in this video lecture of 4.1, I'm going to break it up into two parts. The first part, I'm going to talk about how light has characteristics of both particles and waves. And then when certain frequencies of light strike a metal, electrons are emitted in something called the photoelectric effect. And then I'm going to end it with talking about, well, geez, light, certain frequencies can strip electrons away from metals, but not all frequencies. So there's this idea that light can carry certain quanta or packets of energy. And then in part 2 of 4.1, we'll talk about Bohr's model and how that was kind of the starting point, but it doesn't work for all the elements. So remember J.J. Thomson, when they first thought of what an atom is? J.J. Thomson was the one with the cathode ray tube with that green light, that beam of electrons going through the cathode ray in a vacuum. And then he noticed that with the magnet, it would repel. Okay, so J.J. Thomson's like, okay, so negatives have this negative charge and they are a part of atoms, and we know that there's this positive charge because they're tend to be neutral. So I'm going to say it's kind of like this plum pudding model where the electrons are kind of like the fruit or the raisins in this dessert. Then Rutherford came along, right, and kind of rearranged it because of his gold foil experiment, how the nucleus, instead of encompassing the entire atom, is actually a small dense area and the electrons were on the outside. But there was this idea of like, wait a minute, so if we have this positive nucleus in the center of our atom and the negative electrons on the outside, well, how come electrons don't spiral into the nucleus? Because opposites attract. And so this really like kind of confused scientists. We don't see that happening, so what's keeping electrons set out here and not crashing into the nucleus? Okay. So 4.1, development of a new atomic model. I'm going to talk a little bit about what light is. And light does exhibit properties for both being a particle and a wave. Now, before the 1900s, scientists thought light behaved solely as a wave because you could like reflect it, diffract it. You could it just kind of behaved like a wave. And so light is part of the electromagnetic spectrum. Okay, which is your radio waves, your microwaves, your infrared, your visible light, okay, ultraviolet, X-ray, gamma rays. And the electromagnetic wave shows all types of the electromagnetic waves that I just listed. And all of these waves move at a constant speed in a vacuum. Okay, and that's the speed. 3.00 times 10 to the 8th meters per second. Now, in a vacuum, this is their speed. When you put them through different mediums, that speed does vary. And these electromagnetic waves are arranged according to wavelength and spectrum. So I'll just slide that up for those trying to take notes. Wavelength and spectrum, frequency. And so your bigger wavelengths, like your radio waves, would be way over here, and then that wavelength is going to get smaller, until you get to your gamma rays. Frequency is the opposite of like wavelength. Frequency, if you have your large wavelength over here, that means you have a lower frequency, okay? And your smaller wavelengths means you have a higher frequency. So it's kind of looking at the number of like waves in a set period of time. So the more waves you have in a set period of time, the higher the frequency. Well, if you have small wavelengths, you can get more waves in a set period of time, so you get a higher frequency. Okay, so wavelength is denoted by the symbol called lambda, and it is the distance between corresponding points on a wave. So from crest to crest, or you can say from trough to trough, or you can say from this point to this point. That would be a wavelength, okay? And we can use various units, okay? The unit is going to be some type of distance, meters, centimeters, and nanometers. And nanometers tend to be the waves that we do encounter in the problems that we will talk about here. Frequency is the number of waves that pass in a given point in a specific time, usually 1 second. And if it's like 1 second, then you know, we use the hertz. So how many waves pass through that 1 second? So like 500 hertz wave means that 500 waves pass through that point in 1 second. Okay, so that's kind of how that's measured. So here, as I was talking about the long wavelength, large wavelength, okay, low frequency. But as we shorten the wavelength, we get a higher frequency. So the trend is an increase in wavelength, okay, we'll see a decrease in frequency. So this is an inverse relationship. So if I see a decrease in wavelength, what can you say? What can you predict? An increase in frequency. And so the equation between wavelength and frequency and the speed of light is this, okay? C, which is the speed of light, okay? And then lambda and V. So if you're wondering how to write that equation, hold up here, let me get my marker. So C equals lambda times V, okay? But depending on what you are solving for, you know, you could just cover up the variable. So if you're trying to find like wavelength, okay, you'd cover up lambda and you would take the speed of light divided by frequency, okay? Or if you're trying to find frequency, cover up the V, I take the speed of light divided by lambda, okay? So that is the equation there. C equals lambda times V. Okay, so now I'm going to talk a little bit about the particle description of light. And before, like I said, in the 1900s, people thought that light was a wave, okay? And there's this idea of this wave theory. Waves behave as a wave. Oh, shoot, that's a typo. Light behaves as a wave most of the time. Actually, I can just cross that out right now because that's embarrassing. Can't believe I didn't notice that until now. Light behaves as a wave most of the time. It's categorized as electromagnetic because of both of its magnetic and electric forms, which I did not talk about that in that diagram. So the EM spectrum has two components. It has a light, okay, component and a magnetic component. And usually I do an experiment with polarized lenses to demonstrate how it's got these two waves perpendicular to each other, and how polarized lenses, they block out one factor of that and allow the other one to go through, and how if you overlap polarized lenses and you like rotate them in the right way, you can completely block out light. Okay, and so light waves have both wavelength and frequency. Now, in this experiment, okay, according to wave theory, light of any frequency should be able to eject an electron from a piece of metal, okay? So in this, oh, shoot, I forgot I did not have my arrow. Embarrassing. Okay. Okay, so in this picture here, we see you have this strip of metal, okay? It's just a metal plate. Now, metal tends to have like a sea of electrons. So the electrons are just not held as loosely anymore. And this is why metal is a great conductor. And they said, okay, so if I shine this light, I should be able to like strip some electrons and connect the circuit. You can see how they have this battery source here, but the circuit is not completed. And so if electrons like jump, okay, I should be able to complete the circuit. Now, they noticed that if the frequency of light was below a certain minimum, no electrons were emitted at all. Okay, so what they were trying to do is take different frequencies of light and make them hit this piece of metal and figure out, hey, which frequencies do emit light? And they noticed that red light does not. That's the lowest. Okay, green light, some, blue light, a lot. And that's because blue light has a shorter wavelength, higher frequency, and green, is kind of in the middle. Roy G. Biv. So if light, if it had to be a certain amount of energy, how could we measure that energy? Okay, and so Max Planck was doing research with emission line spectrums. He was basically heating objects up and then studying the light that was being given off by that object. So if you take like an iron poker, right, you're playing in the fire or you leave it in the fire and then you take it out, it's like red, right? It's glowing, it's giving off light. And so he was like, that was his study. What he was looking at was emission line spectrums or black body radiation. So he proposed that hot object does not emit electromagnetic energy continuously if the energy was in the form of waves. So he was like, maybe it emits energy in quanta, and that there's this minimum quantity of energy that could be lost or gained by that atom. Kind of confusing, but basically he was determined to quantize the energy that was being lost by that object. And from Max Planck, we actually do have an equation to measure a photon, okay? And so that equation is E equals hv. Now, E equals hv, it can be this, but what happens if you're given wavelength? Then how could you use that? Well, they are related to like the other equation, the C equals lambda times V. So E equals h times V, which is the frequency, or you can use this equation because it's like in the problem down here, I give you lambda. E equals h times c divided by lambda. Okay, so it depends on what you're given. If you're given frequency, great. Plug it in, take it times h, which is a constant. This is the number for that, and you have your answer. But if you're given lambda and not frequency, then you have to use the speed of light. And you have to make sure that the wavelength and the speed of light, which is 3.0 times 10 to the 8 meters per second. Well, here we're given nanometers, so we do have to do a conversion. So in this example here, it says wavelength is 500 nanometers. Well, what's a nanometer? Nanometer is 10 to the negative 9. But that means I would have to move the decimal place over 9 places. And when I do that, I end up with, 5.00 times 10 to the negative 7 meters. That's a 7, okay? All right, so there's my wavelength. And then I have H. Oh, God. Okay, I'm not going to type that in. I'm just going to leave it as H. The H is right there. And then I have C, okay, which is 3 times 10 to the 8 meters per second. Okay, it is too early in the morning for me. 10 to the 8 meters per second. All right, and then the unit over here is, I'll just put in parentheses, joules times seconds. So just looking at this, you can already see which units are going to cancel out. Okay, S, the meters, and then you're left with joules. And joules is an amount of energy. So I'll plug this into my calculator here. 6.626 times 10 xy key to the 34 negative, and the parenthesis times the speed of light, 3 times 10 to the 8 divided by parenthesis 5 times 10 to the 7 negative. All right, so my answer, I have 3.9 9756. I have 4 sigs, so I'll go 3.976 times 10 to the 19. Oh, that's a negative 19 joules. There, so we quantized that tiny little photon there that had this wavelength. All right, so Albert Einstein comes along and he decides to expand, excuse me, on Planck's theory of quantum theory of light. And he's like, hey, remember, there's this dual wave particle nature. Okay, we know that it behaves like a light. Okay, it's got wave-like properties, but it also has a particle nature to it because it can like physically knock off an electron. Okay, so it has both particle and light properties, and each particle carries that quantum of energy, aka that's what a photon is, a packet of energy. It has 0 mass, but it carries an amount of energy. So he was able to explain the photoelectric effect by saying that the EM radiation absorbed by that matter, I thought I had my arrow here, is absorbed only in whole numbers of a photon. Okay, so basically Albert Einstein's coming along and he's saying, hey, remember, it's a wave, but it's also a particle, and that particle has an amount of energy, and that energy is a whole number. Okay, so in order for electrons to be ejected from that piece of metal, like I said, it has to be struck by a single photon that has the minimum amount of energy. So you notice up here that we have our frequencies, and then those are the energies. Okay, and electrons in different metals, they're bound more or less tightly, so different minimum frequencies are needed. And because of this idea that wow, light behaves like a particle and has to like physically hit that electron straight on. You know, you can kind of think of it as like you're at a carnival, you know, or the Midway, and you're going to play a game where you have to knock down like milk bottles or something. I mean, you have to like physically hit that target for it to be ejected. Now, because of his work, this is revolutionary. Okay, now people are thinking, wow, this whole universe is composed of tiny discrete chunks of energy and matter. And I know it sounds really confusing, but all we've talked about is how electrons, okay, light, behaves as both waves and particles. And this experiment, the photoelectric effect, that shows that light does have particle-like properties, and that you can measure the amount of energy through Planck's constant, okay, the E equals H times V. Okay, so that does it for part 1. And then we would read up to that, and then I'll make another lecture video here for part 2.